Hi there, my name is Ian, and I'm going to run through a whole bunch of exam questions on linear programming, one of the most exciting bits in paper 1. Now, a whole lot of you are going to say, am I crazy? Linear programming exciting? Yes, it is. It's one of the most widely used pieces of maths, which we do at school, that is used in business today to help maximize profits, minimize costs, and to use human resources and other resources that are scarce to the best of their ability. Now, the way I've structured our 90 minutes is I'm going to take questions, sample questions from all over the place and do them, different types of questions. Now, the first question I've got is where we're given a whole bunch of words, a little story, and we have to convert that into equations or inequalities. So let's get going. It starts off by talking about a farmer who needs to build more dams to increase the carrying capacity of his farm. That's just putting it into context. No maths involved there, and we don't even have to know what the farmer's name was. He needs at least 12,000 kilograms of sand. So he needs more than that. At least 400 kilograms of gravel. So the least he has is 800 kilograms of gravel. Needs more. And at least 480 kilograms of cement. His local hardware store has strong-bulled and fast-bulled crates that are pre-packed. And they've got different amounts. Strong-bulled has 600 sand, 200 gravel, and 60 cement. Fast-bulled, on the other hand, has 200 sand, 200 gravel, and 160 kilos of cement. All right, those are the important numbers that we need to work with. So let's have a look how we can turn that story into a bunch of constraints. Now what happens is that they tell you which one should be X and which one should be Y. In real life, you would make your own decision on which should be X and which should be Y. But it really helps the markers if all the answers look pretty much the same. So let's start. If we have a look at sand, and what I'm going to do is I'm going to rub out my colors, and I'm going to just talk about sand for starters. I need 600 sand from Strongbow and 200 sand from Fastbulled. And what do I need with sand? I need 12,000 kilos. So if I have X Strongbulled, I will have 600x kilos of sand. And if I add that to Y packets of Fastbulled, 200Y, I'll have 200 times Y kilos of sand. And how much sand do I need? Well, I need at least 12,000, so I need more than that. So that's why the amount that I buy has to be more than, can also be equal to, 12,000 kilos. And there's my first constraint. Let's change pen color and have a look at the next one. We're going to look at gravel. Gravel, we've got to have 800 kilos of gravel. Well, Strongbulled gives me 200 kilos. That's my X. Fastbulled, my Y, gives me 200. And I've got to have at least 800. So that's quite great, because if I have 200x plus 200y, that has got to be bigger than or equal to my total amount of gravel I need, 800 kilos. Now some of you are looking at this and saying, okay, so we could buy no x's and we could buy 4 y's. Yes. And that would fit this one single constraint. But remember, what linear programming does is it takes a whole bunch of constraints and works out which one is going to be the best, or which options we can use. Let's look at our last little constraint. Well, our last constraint was talking about cement. 480 kilos of cement. Well, Our x gives us 60. Our y gives us 160. So let's write our constraint. So 60x plus 160y must be bigger than or equal to, and how much cement did I need in total? 480. And those are my three constraints. Now, some of you have heard of implicit constraints, constraints that are implied within the situation. Have a look at this situation. Could you go into the hardware store and buy half a crate of Frostboard? No, it's pre-packed. That's why it's probably cheaper. That's why the hardware store made it that way. So in this case, both my x and my y have to be elements of the whole numbers. I can buy none. I can buy as many as I like, but I've got to buy in units. And those are my constraints. Let's move on to the second question. Once again, here we're going to look at words, and we're going to change those words into equations or inequalities as they actually are. The owner of a bus takes tourists, adults and children on a tour of Soweto during the World Cup. Fantastic. That gives the situation, that gives a scenario. No, we don't have to worry about that. Although just think about implicit constraints. Tourists, you're going to have whole numbers. You can't have half a tourist running around. Do no one any good. He's allowed to provide the tour as long as the group consists of less than 60 people. Aha, less than 60 people, some information. And subject to the following constraints. There must be 36 persons at least 35 persons in the groups. It's got to be 35 or more. But not bigger than 60. There must be at least 6 adults in the group. And there must be not more than 14 adults. So it looks like there's going to be adults and children. And if x represents the number of children and y the number of adults, write down all the constraints. Well, let's start with the first one. Got to be less than 60 people. So we know that the number of children, which is x, plus the number of adults must be less than 60 people. Not less than or equal to, got to be less than 60 people. Now, if you were asked to do a model of this, technically, your line would be a dotted line. Let's look at our next constraint. There must be at least 35 people in the group. At least 35 persons in the group. So x plus y must be bigger than or equal to 35. Second constraint. Let's look for our third one. At least 6 adults in the group. Now, adults is y, so y must be bigger than or equal to 6. No more than 14 adults. So we could write this as another constraint, or for those of you who would like to, you can combine those two constraints and say that y must lie between 6 and 14. Now, it doesn't matter which way you do it. If you want to do the two constraints or put the two into one, it's absolutely fine. Whichever way you prefer to do it is fine. And those are our constraints. Technically, let's look at it again. We know that x and y must be elements of the whole numbers. That's it. Right. That was the question in its entirety. All you had to do is write down the constraints. They didn't want you to do a model. They didn't want you to optimize in this one question paper. Let's see what happens in the next question. 2 types of surfboards, airbrushed and clear. 8 hours to make an airbrushed board and 4 hours to make a clear board. So here they're referring to human resources. The company can only work for a maximum of 72 hours a week. So all your guys, 72 hours a week, that's it. Surf's up. At least 10 boards must be produced per week, and no more than 10 clear boards can be produced per week. Quite a few constraints. Let's do them one by one. They tell us X is airbrushed boards and Y is clear boards. So, 8 hours to make an airbrushed board. Is that a constraint? Yes, it is. Because if I have 8x plus 4 hours to make a clear board, that's the number of hours that my factory can work for. And it can work for a maximum of 72. So this must be less than or equal to 72. That's my first constraint. My second constraint is about the boards themselves. At least 10 boards must be made per week. Doesn't matter if they're clear, doesn't matter if they're airbrushed, we've got to make more than 10 boards a week. At least 10 boards a week as we go out of business. Let's look for our other constraint. No more than 12 clear boards can be produced weekly. Clear boards is Y. So we can't produce more than 12. So Y must be less than or equal to 12 clear boards. Now, what is the implied constraint, the implicit constraint? Now, in my opinion, if you on Friday afternoon are halfway finished with a clear board, you can leave it until Monday morning. So here, X and Y are elements of the reals. It doesn't matter if you leave half a board unfinished over the weekend. It'll still be there on Monday morning. Right, there are our 3 constraints and our 1 implied constraint. Hope it's getting a bit easier to read between the lines and get the inequalities. Right, moving to question 4. Now, question 4 deals with an entrepreneur in the Lowveld making 2 types of braai stands. Sounds like a good option. X braai Impala braai stands, probably the small ones, and Y kudu braai stands, probably the ones where you can put a whole family's cheese inyama on in one shot. The factory cannot manufacture more than 100 Impala stands. Okay, so we know straight away that X has got to be less than or equal to 100. Our first constraint. And it cannot manufacture more than 60 kudu sets per month. So Y has got to be less than or equal to 60. So if we had to do a model, our model is already having a constraint at 60 and already having a constraint, sorry, that's 100 over there, and already having a constraint with 60 over there. It's going to be between 0, 0 and that. It's already being constrained. The maximum number of 140 sets of both types can be made each month. So we know that X plus Y must be less than or equal to 140. A farm produce store, possibly one of those great ones in the Lowveld, has a standing order for 10 Impala and 30 kudu sets per month. Now, a standing order means that the factory has to provide that every month, at least that. It's a standing order. We want 10 and 30. So we know that X is going to have to be bigger than or equal to 10, and Y is going to have to be bigger than or equal to 30. A standing order means it happens every single month. So 10 is the minimum number of Impala sets they can make because of this one shop in the Lowveld. 100 is the maximum they can make because of your factory constraints, size, raw materials, some reason, I don't know. So it's going to have to be between 10 and 100, somewhere there. Now, just making a small model on the side, that would be your 10 over there, and that would be your 30 over there. So already, the region that we're looking for has decreased. And eventually this question could go on to say, if the profit on Impala or the profit on kudu is such and such, how much are you going to make? What is going to be your best profit? And then you'd work it out. Now, the last constraint, second last constraint. The number of kudu sets made each month is not more than twice the number of impala sets made each month. So we know we're talking about kudu sets, and we're talking about twice the number of impala sets. Just have a look at that again. The number of kudu sets is not more. Okay, so it's not more, so it's going to be less than or equal to twice the number of impala sets. So this is going to be less than or equal to. That's our second last constraint. What are our implicit constraints? The constraints implied by the situation. Well, at the end of the month, do we have to have every braai stand complete, or could we wait until the first of the month to carry on? Yes, second option's right. So in this case, X and Y could be elements of the reals. You don't have to have completed braai stands, unless, of course, your scenario, the picture, the storyline, says that you have to finish what you started every month. Now, that's the first kind of question that's going to be asked, is taking all the words and putting it into constraints, putting it into inequalities. What I'm going to be doing now is I'm going to be looking at a model, and you're going to have to take the model and put it into a system of inequalities. So you're going to have to take the straight line pictures and write your inequalities. Let's look at question 5. The sketch represents the feasible region for a system of inequalities. No storyline here, just tells you exactly what's happening. Write down all the inequalities which apply to this graph. So, what have we got? We've got 1, 2, 3, 4. We've got a whole bunch of constraints. Why have they done this for us over here? And let me change pen so we can actually see what I'm doing. Why have they done that? Well, the X and Y intercepts are both 0. There it is. And remember, if you are if you're finding the equation of a straight line, you're going to need at least 2 points. So that's why they've done that there. So what I'm going to do is I'm going to start off with a line, and I'm going to label it ED. Why am I going to label it? So that I can keep track to make sure I've done all my constraints. In this case, we can't use the fancy equation x over a plus y over b is equal to 1. We've got to use traditional methods. Well, I know y is equal to mx plus c. And in this case, my slope is 1 over 2, 10 over 20, a half. And my c value is 0, so there is my first equation. But this isn't an equation. This is actually an inequality. The feasible region is above this line. The y values we want are bigger than the line. They're above. They're on top. So I'm going to change this, and I'm going to write that the y is bigger than and equal to a half x. That's my first one. If I have a look at this line over here, AB, horizontal line, the horizontal line AB, well, horizontal lines always have y equals. Now, what was the y-intercept? It was 40. So we know y is equal to 40. That's the equation. But we're wanting the inequality. Now, here the values we want lie below the line. So y is going to be smaller than the line. So y is going to be smaller than or equal to 40. Let's do the next one. I'm going to choose this line here, this line BC, and it's got a y-intercept of 60 and an x-intercept of 60. So what I can do is I can write x over 60 plus y over 60 is equal to 1. Yes, it's as easy as that. X over the x-intercept plus y over the y-intercept gives you 1. I'm going to make it look pretty, and then I'm going to turn it into its inequality. So multiplying through by 60, I get that y is equal to minus x plus 60. All right, let's just have a look where the feasible region lay. The feasible region was lying underneath the line. It was smaller than the line. So we don't want y equal to, we want y smaller than minus x plus 60. Shame, poor y. That was the line BC. Okay, the last two are these two vertical lines. This one over here, AE, and this one over here, CD. Vertical lines, they both are involved with x only. Now, I'm going to do it first with 2, and then I'm going to put the 2 into 1. Your option, you can do 2 and leave it as 2, or do it as 1. Not a problem. So the line AE, x has got to be bigger than or equal to 10. Bigger than or equal to 10. Why? Because it's going to be bigger than. The feasible region is bigger. The other one, this other line, and it's called CD, is x is going to be less than or equal to 30. If you would like to pop those two into a single inequality, please feel free to do so. X lies between 10 and 30 inclusive. Right, those are the constraints. As easy as that. Let's move on. Question 6. The shaded area represents the feasible region for a set of linear constraints. Right? No scenario, straight in. This is a model. They want the constraints. The labels have been labeled for us, A, B, C, D, and E. Fantastic. Find the equations. Right, well, here we go again. I'm going to choose these two horizontal lines first. I think they're probably the easiest to do. So what do we have here? We have that y is going to lie between 30 and 10. So y is going to lie between 30 and 10. Now, how did I know it lies between 30 and 10? Well, that's where the shaded region is. It's bigger than 30. Y is bigger. Sorry, it's bigger than 10. Bigger than 10 because the feasible region is on top of the line y is equal to 10, and it's below 30. However, if I think back to the question, they're saying they want each respective equation. So they don't want it like this. They want line E to be y is going to be bigger than or equal to 10, and they want line D is going to be y is less than or equal to 30. So even though in the previous case we could have put the two together, in this case we're not allowed to. Right, the next question, or the next line I'm going to do is line A, has a y-intercept of 40 and an x-intercept of 20. I'm going to do it the newfangled way. Line A. What's my y-intercept again? It was 40. So, sorry, just starting again there. We've got x over 20 plus y over 40 is equal to 1. Yes, and I know I can write that equation as y is equal to minus 2x plus 40. However, we're looking for the feasible region. We're not looking for the equation of the line, but it's an inequality. So where does this inequality lie? Well, on line A, which is this line over here, y is bigger than the line. It's above the line. So we want y to be bigger than or equal to minus 2x plus 40. That's line A done. Let's have a look at line B, this line over here. A y-intercept of 50 and an x-intercept of 50. So line B has a y-intercept of 50 and an x-intercept of 50. Now, I know that most of you will already be able to write down that y is equal to minus x plus 50, and you probably didn't need any working for that either. Once again, let's check our inequality. It's below the pink line. It's below the pink line. So y is smaller than or equal to this minus x plus 50. Right, we've done A, B, we haven't done line C. Line C is this vertical line over here. I'll go back to green. It's that vertical line there, so it's an x equals line. It's smaller than the line, so we want the x's smaller than the line, and the line is 30. So line C, x will have to be less than or equal to 30. There are our constraints. Easy, isn't it? Putting an equation into an inequality. All you've got to do is see, is the feasible region above the line or below the line? And then fill in the corresponding inequality. Let's move on. Here's another question. Exactly the same as the one before. Given the constraints which are described by the model below, no scenario, no braai stands, no surfboards, straightforward, let's work out the equations of the lines. Well, if I have a look at this line over here, which is MN, that comes down to an x-intercept of 10, and my feasible region is bigger than that line. X has got to be bigger than or equal to 10. That's my first constraint. Let's have a look at another one. This one over here, the line NK. So the line NK. Let's just be technical and good about how we write down our answers. So that first line was the line MN. It always helps to label exactly what you're doing, because then you know that you've done it all, and the marker can find your answers easily and give you the credit you deserve. So it's good exam technique. Right, the line NK was a sloped line with a y-intercept of 60 and an x-intercept of 30. And what I'm going to do is I'm going to do this one the slightly more traditional way. I know that my change in y is 60 and my change in x is 30, so m is going to be 2. So y is going to be equal to 2x plus 60. However, it's not an equation, it's an inequality. And the graph is lying above. The feasible region is lying above our line. So y is going to be bigger than or equal to 2x plus 60. Now, I don't know which way you prefer. You might prefer the slightly more traditional y is equal to mx plus c way, or you could try the x over a plus y over b is equal to 1. Whichever way you prefer, go for it. Let's have a look at this line over here, the line KL. Well, they only give us a y-intercept. They don't give us the x-intercept, but they do give us a second bit of information. So from the point 0, 10 to the point 60, 20. Well, I'm going to do it the old-fashioned way because I don't have my two x-intercepts. So the line KL, and I'm just going to redraw the triangle over here. So that was the point 0, 10. And the other point over there was the point 60, 20. Working out my slope, well, of course you can do it with the equation. Most of you are doing it in your heads as we talk. The x's change is 10 and the y change is 60. So the slope will be equal to the change in y over the change in x which simplified will give you 6. So here y, and you'll have a 6x plus 10, 10 being your y-intercept. Now, the feasible region lies above this line. So in this case, y is bigger than or equal to 6x plus 10. Let's have a look at our last constraint. This line over here, mn. Well, we've got our y-intercept, we've got our x-intercept, they're 80 apiece. So I know the slope is going to be minus 1, and I know my y-intercept is 80. No working, it's fine. The feasible region is below the line. Below the line, so y must be less than. Shame, poor y. And there we go. There are 4 constraints. Now, I'm going to take a moment out of here and talk about maximizing and minimizing. What you'll notice in this feasible region over here, there are 4 vertices. There's a vertex there. There's a vertex over there, a corner where the lines meet in the feasible region. There's a vertex there at M, and there's a vertex there at N. Let's say this scenario was talking about making braai stands. If we were looking for a profit, we would be looking for a maximum profit. Where do you think the maximum profit would be? Well, it's on one of the vertices. So it could either be at M, or perhaps it could be here at L. If, however, the optimization question was dealing with costs, we're looking for a minimum costs. Where would we find the minimum costs? Well, yes, there we would find minimum costs at N, or perhaps at K. Your optimization always happens at the corner of the feasible region, at the vertex of the feasible region. So for those of you who are not quite sure on how this optimization line works, I'm going to suggest that you take your vertices of your feasible region and substitute those points into your profit equation that you have to write. Well, here we got a question. A factory produces X plasmas and white flat screen TVs. The profit is $750 on a plasma and $1,250 on a flat. Write down the objective function, the thing that we're trying to find, representing profit. Here we're trying to work out, we've got all our constraints. Our constraints are done. This would traditionally be the last little bit of the question. Well, let's write down our profit. Profit would be equal to how many X's? What's our profit on X? 750. So for every X we make, we get 750 bucks. And for every flat screen we make, we get 1,250. There we go. 1 mark. Fantastic. How is this going to help us if we have to do an optimization on a model? Let me show you. Let's say our model landed up with a feasible region that looked something like that. There it is, colored in. What I'm going to do is I'm going to take the X and Y value at the vertices and substitute it into my profit equation. That vertex, that one over there, and that one over there. It's very simple to do. Use your calculator to do it, and you can test quite easily. However, you might prefer to do the line and you slide a line up and down. How would we do that? Well, we're going to have to change our profit equation into a y equals so we can get the slope. So this equation over here, we're going to have to change. So we get 1250y's is equal to negative 750x plus p dividing through negative 750 by 1250x. And there we have our slope. Let's double check in the calculator what that is. Well, we've got 750 divided by 12. Let's just double check our number, 1250. And as you can see, I've mucked that up. I've put that as a fraction, but there we go, 3/5. So the slope of our profit line is 3/5. So what we need to do is we need to go to our graph and draw a line that is a change of y of 3 and a change of x as 5. And there we have our profit line, 3/5. If we then keep drawing our lines parallel to that, look, they've hit the vertices there, they hit the vertex there at some stage. But is that going to give us the best profit? No, not at all. We'll notice that now it hits one of the maximum type vertices, but is that the best one? No. This one eventually will give us our maximum profit. So, when we're looking for our objective function, our optimal solution, the best solution for us, either minimum costs, maximum profit, we can either test the vertices of our feasible region, or we can take our profit equation, rewrite it as y equals, get the slope, and take that slope and slide it up. Where's it going to give us minimum? Where's it going to give us maximum? And there we can see at which point, read off the corresponding x and y values, what is going to give us our optimal solution for our question. Right, here we have a question which talks about our Plasmon flat screen again. We've gone through it in theory. Here we've got it. They gave us a model. So what we had is our profit was equal to 750x's plus 1250y's. And they've given us a feasible region. There it is. There's the grid. What we have to do is work out our profit. 750x's plus 1250y's. And that's going to give us our profit. What I'm going to do is I'm going to do a little table. I'm going to have my x's, I'm going to have my y's, and I'm going to have my profit. And from that, I'm going to see which is going to be my best profit. Well, the first point I'm going to look at is that point over there. That's going to be the point 1, 2, 8. So my x is 2 and my y is 8. Let's go and look at the next point. That point over there. 2, 3, 4, 5. That's going to be the point 5, 8. So x is 5, y is 8. And the last vertex of my feasible region will be 8, 2. 8 x's, 2 y's. Now what all I need to do is I need to take my calculator and pop these numbers in and work out what my profit is going to be. So, here we go. I need 750 times, and the first one was 2, plus 1250, and in the first case, it was going to be 8. I've put my x's in as 2, my y in as 8, and that's going to give me a profit of 11,500. 11,500. Go backspace. My next x value is 5, and my next y value will be 8. 13,750. 13,750. Ha! Better profit. Let's see if my third vertex gives me the best profit possible. Well, my y value is 2, and my x value is 8. Hold your breath. Okay, definitely not. 8,500. So there we go. Quite easy to see from our table which gives us our best profit. Our best profit and please make sure you write the question out. Don't let the marker have to scrabble through your workings. Write it out neatly. For maximum profit, manufacture 5 X's. Well, what were the X's? Let's just go back and make sure X's were plasma. So 5 plasma and 8 flat screen. And there we go. Isn't this table method a lovely way to use to work it out? I much prefer it. Now, someone out there is going to say, but what happens if you get the same profit for 2 vertices? Well, let's have a look at that option. Because this is a beautifully drawn grid, I'm going to use this exact same grid to answer that question. Let's say from that point, point A, I got a profit of 1,000 Rand. And let's say from that point, point B, I also got a profit of 1,000 Rand. What does that mean? That means that anywhere along the line A, B will give you a profit of 1,000 Rand. It'll be the same profit. So, how are you going to decide which is going to be the best solution for your company? Your choice. In this case, and here we need to look at the screen quite closely, that point at point A does have integer values. That one there has integer values, that point has, and so does B. So they could say what 4 sets of values would give you maximum profit. Very, very rare question. And I'll just repeat the question so that we're all on the same page. What happens if 2 points, 2 vertices on the feasible region give you the same maximum profit? Then anywhere on that line segment, any option will give you maximum profit. Let's move on to the next question. Here we go. Stacy runs a cottage industry that manufactures chocolate sauces. Yum. Ooh, vanilla extract from Mauritius and some other secret items. Recipe X uses cream and melted bar ones. Recipe Y uses cream, almonds, and Lindt chocolate. Lovely question. Makes us rather hungry though. If a profit of 200 Rand is made on every litre of recipe X and 150 on every litre of recipe Y, write down an equation for weekly profit. Quite straightforward. Profit is equal to 200X plus 150Y. Here's our profit. Done and dusted. Same question, and they gave us the grid. Now have a look here. Here are 3 vertices that we can clearly read off from the model that they gave us. So all we're going to do is we're going to take our profit, and let's just go back so we can remember what it is. 200X plus 150Y. Our profit was 200X plus 150Y. And we're going to make a little table. We've got our X values, our Y values, and our profit values. let's have a look at the vertices of our feasible regions. Well, 10, 20, 30, yes. So that's 10. This point over here will be the point 10, 40. So the first one in, x is 10, y is 40. Okay, right, let's have a look at our next vertex. It'll be this point, which will be 30, 20. Great. 30 x's, 20 y's. This point over here will be the point 2020. Now, the only reason I'm doing this point is because I like to do all the vertices. Then I know that I've covered them, all the options. I'm sure that you're already saying, there is no ways that that can give you maximum profit. I agree with you. I'm just going to do it for the exercise. So we've got 2020. Right. Once again, pop this into our calculator. So we've got 200 times 10, and we're going to have that added to 150 times 40. Going to give us a profit of 8,000. Let's do our next numbers. Well, 30 liters of X and 20 liters of Y. You think it's going to give you maximum? Let's wait and see. Dunk, 9,000. Yes, 9,000. And just for the exercise, just because we could, we'll do 20 X's and 20 Y's, and that confirms that definitely does not give us our maximum profit. So this point over here, 3020, that gives us our maximum profit. So once again, we'll write it down, maximum profit at 30 liters of X type and 20 liters of Y type. Right, now that we've got that answer, what I'm going to do is redo the question. I'm not going to use a table, I'm going to use my optimization line. I'm going to turn my profit equation into a y equals, get a slope, and show you how you get exactly the same answer with a different technique, possibly the one you've been taught. Let's write down our profit equation. Well, profit is equal to 200x plus 150y. Converting that, I get 150y is equal to minus 200x plus p, dividing everything by 150. I get that my slope is 200 over 150. Just double checking what negative 200 divided by 150 is, gives us negative 4/3. That is going to be the slope. Our slope is negative 4 over 3. Well, that's great. If we go back to our graph, our model, negative 4 over 3, we could use 40 over 30. I think that'll be much better. So using 40 over 30 as our line, we draw in our first line. There it is. Now that is our profit line. We're going to take that line and move it, keeping a slope of 4 over 3, negative 4 over 3, all the way up till we hit the vertices. Right, let's go until we hit our feasible region. Aha! There's our first one, 2020. Is that going to give us maximum profit? Absolutely not. If we were looking for minimum cost, that would be our point. Moving it up a bit more, there we go, the 1040. Hits the 1040, the vertex, the feasible region. Is that maximum profit? Not yet. And using our line going up, there we go. We've hit it. Bingo. X marks the spot. 30, 20 gives us a maximum profit. So let's just run through this again. I'm going to zip down to the table. We wrote our profit equation, and then we tested every vertex of our feasible region for the maximum profit. And yes, there we got 30 X's and 20 Y's for our maximum profit. That's one way to do it. The other way to do it is taking our equation, finding the slope of the line, in other words, putting it as y equals, and taking that slope, that negative 4/3, we go back up to our grid, and what I did was I put in the line 40, 30, the green line over there, and I slid it upwards, keeping that slope. First to the one point of the vertex, the one vertex of the feasible region, then the next vertex of the feasible region, and finally the best option, the best vertex, the one that will give us maximum profit. Now that's how you do optimization. Right, I'm going to move on to the next question, and this came from the Department of Basic Education, November 2010, talking about braai stands. Great, love it. This is what I call a complete question, where you have the story, you've got to write down the constraints, you've got to make a picture, got to make a model, got to shade in a feasible region, and then we've got to answer questions about it. Whether it's, can you manufacture so many braai stands of type X and so many of type Y? Or what is going to be our maximum or our minimum? Haven't read the question yet, so we'll get there. Let's do this together. The factory produces two types of braai stands, type A and type B. Good news. 1 hour of machine time and 3 hours for welding and finishing for type A. So the first thing is we've got is machine time. And then we've got 3 hours for welding and finishing. The second one is 2 hours of machine time and 1 hour for welding and finishing. I wonder what the finishing is. Maybe smoothing off the rough edges, bit of liquor paint. Yep. What they have here is they're now telling us that no more than 28 hours machine time. Right? Maybe we don't have the tools, maybe we don't have the electrical supply, maybe we don't have the workers that can work more than 28 hours a week or a day. And the second bit is 24 hours, and being consistent, 24 hours for welding and finishing. Now, what you'll notice is that I've used two different colors. I've kept pink as machine time and yellow as welding and finishing, because those constraints are going to have to work together. Here we go. Write down the constraints terms in terms of X and Y. Now, X is type A, which is great. So, let's talk about our machine time. Machine time. Now, machine time, what is the maximum? Machine time is 28 hours maximum. Okay? Type A is 1 hour. Type B will be 2 hours. And we can't have more than 28 hours of machine time. 28 hours is our absolute maximum. That's machine time, the one I've done in pink. Let's move on to the welding and finishing. Well, welding and finishing, they say that we have a maximum of 24 hours. And going back to the question here, type A is 3 hours maximum. Sorry, 3 hours, takes 3 hours of welding and finishing for type A's. Type B, it's 1 hour for welding and finishing. And there we go. Those are the only constraints that we have to worry about. They don't ask us for implicit constraints, all right? And if you wanted to, you could put in your implicit constraints. So x and y are elements of the reals. Why do I say reals? Once again, you can have a half-finished product on the factory floor and knock off for the afternoon and come back tomorrow and finish it off. 10.2. 10.2 asks us to represent these constraints on the grid provided and shade the feasible region. So if we have a look at them, the first one was, let me change my color ink, was 3x plus y must be less than or equal to 24. What's the quickest way to draw a straight line? Let x equals 0, find y. Let y equals 0, find x. Let's hear the click. Let x equals 0, find y. Let y equals 0, find x. Okay, so cover up the y, and we got our x-intercept as 8. There we go, that's our x-intercept. Cover up the x's, and our y-intercept is 24. So our line is going to go like that. There we go, first line. The next inequality that we wrote down was x plus 2y is going to be less than or equal to 28. Cover up the y, and we have the x. Cover up the x, and we have the y of 14. Join the two dots, and there's our line. Now what we have to do is to color in the feasible region. Now I know this is where some of us have trouble. So what I'm going to do is I'm going to take a test point. The test point I usually use is the point 0, 0. Now, I'm sure you're wondering why 0, 0. Well, it's the quickest way to work with numbers. If you multiply by 0, you get 0. So if I put 0 into my first test point, or my first inequality, is 0 less than or equal to 24? Yes. So it must lie below this line over here, because it does lie in that region. Let's pop a test point into the next inequality. 0 plus 0 is 0. Is 0 less than or equal to 28? Yes. So it must lie below this line over here. Now, where do these two constraints happen at the same time? Yep, you've got it. This whole section over here. And what I'll do is I'll just rub out those other two pink arrows. Now, what does this mean for us? This means that I've got 1, 2, 3, 4 vertices. The point 0, 0 does fit both constraints. I could sit around and not make any braai stands, and my constraints will be fulfilled. If I look at the second one, which I'm going to label B, this point 0, 8, I could make 0, 8 of type X and 0 of type Y. Yes, once again, my welding as well as my finishing constraints will be fulfilled. And any other option inside that feasible region. For example, I could take the point 2, 2. 2 x's, 2 y's, my constraints will be fulfilled. That's just as background. I've done the question. Let's move forward. Determine the largest number of each type that could be manufactured on one day. We need to go back to our graph and have a look at this. What is the largest number of type A's that could be the type X's, type A's that could be manufactured on one day? Well, that's the biggest value for x that we have. They're not asking x and y combinations, they're just asking the maximum number for each type. So x's would be 8. Our y's in our feasible region would be 14. So x's would be 8 and the y's would be 14. Okay, 10.4. Determine the maximum number of braai stands that could be manufactured. That's talking about a combination of braai stands. Now, having a look at our graph, let's see which points give us the maximum total number of braai stands. Well, we could look at this first point over here, and that gives us 8 plus 0, which gives a total of 8 braai stands. This point over here gives us 0 plus 14, which gives us a total of 14 braai stands. Let's have a look at a couple of other points. You'll notice that the dotted lines are increments of 2. So for example, this point over here is the point 6, 6. And that gives us 12 braai stands. Let's have a look at this one over here. That is 4 plus 12, which gives 16 braai stands. And yes, taking all the points, that is our maximum number of total braai stands that we can have. So 4 x's and 12 y's. So 4x type plus 12 y type for a maximum of 16 altogether. 10.5. If the demand of type A braai stands is at least as large as type B braai stands, determine the maximum number of both types that can be manufactured. And then they ask a question about machine time. What are they actually doing here? They're giving us an additional constraint. This constraint is going to change the feasible region. Probably going to chop half of it away. Let's write down the constraint. Then we'll go back to the graph, fill it in, and then we'll answer the questions. If the demand for type A is at least as large, in other words, the Y type, the type B, is going to be smaller than type A. The X is going to be bigger than or equal to Y. It's at least as large. In other words, you could have 20 type A and 10 type B. Not a problem. But you couldn't have less than 10 type A if you had 10 type B. So that now is an additional constraint. I'm going to go back to the graph. I'm going to pop it in. We're going to sketch our new feasible region. I'm going to write it down here. X is going to be bigger than or equal to Y. Now, what I'm going to do is I'm going to rub out all the other stuff I had, just so that we can see what's going on before I pop this one in. Now you will notice that we can't use our little rhyme of let x equal 0, find y, let y equal 0, find x. We can't use that one because they both go through 0, 0. So what we've got is we've got a point 0, 0 going through 2, 2, 3, 3, 4, 4, 5, 5, 6, 6 over there. Now, if we remember, our feasible region was sort of on the 0 side of those big 2 lines. Let's see if it's going to be above this constraint or below this constraint. I'm going to take a test point. And I'm going to take this test point over here, which is going to be the point 4, 2. Remember the dotted lines are in increments of 4, or in increments of 2. Is 4 bigger than or equal to 2? Yes, it is. So our new feasible region involves that point, and it's this little one over here. A new feasible region. Let's go down and see what the questions were actually asking us. Determine the maximum number of both types. So all we're doing is we're doing 10.4 again, but with a different feasible region. back up to the graph. Well, I'm going to choose this point up here because it looks interesting. That is the point 6, 2, 4, 6, 6, 6. Well, that gives me a total of 12. This point over here will give me a total of 8. This point over here will give me 4 plus 4, which is a total of 8. Looks like 12 is going to be our new maximum with this new feasible region. So writing our answer out nicely, we have 6 type X's and 6 type Y's to equal 12 Bryce-Dan's maximum. Now here's a different kind of question. Here they're wanting you to go back to one of your original constraints and pop these values in. What is the machine time required in this case? Well, we have the point 6, 6. That's the point we've chosen to have the maximum. Let's go back and find the machine time for the machine time inequality that we wrote. Back to the original question. Here we go. 1 hour of machine time for type A and 2 hours of machine time for type B. So 1 hour for type A and 2 hours for type B. Let's go down. So it's going to be 1 for type A and 2 for type B. Well, popping the number of type A's we got into the equation and the number of type B's that we've got into the equation gives us 18 hours. That's the machine time required with this new constraint that we've done. Let's just double check for a matter of interest. What was the maximum machine time we could use? Maximum machine time was 28 hours. So, does this point fall within that constraint? Absolutely yes. Maximum is 28, we're using 18. So the guys who on the machines can have a few minutes break. Right, let's just run through what we've done in this question once again. Because this is a complete question. It's got all the bits and pieces with it. We were given a story. We converted the story into inequalities. We took those inequalities, which are our constraints. We modeled them. We graphed them, put them on graph paper. We modeled them, made a model. We colored in our feasible region, and then we answered questions. Our feasible region was changed with a different constraint, and then we answered additional questions. That was a great question. Let's go on to our next one. Right, question 11. This question was taken from the Department of Basic Education, the February-March exam, 2011. Really recent. Right, all about the World Cup. What a wonderful occasion that was. While preparing for the 2010 Soccer World Cup, a group of investors decided to build a guest house. There's the scenario. All it is words about the whole question. Single and double rooms to hire out to visitors. They came up with the following constraints for the guest house. Now let's just step away from this question for a minute. Why would there be constraints? Well, a group of investors. You don't have unlimited cash available to invest. Why other constraints? Perhaps the ground that you have is too small. You don't have unlimited venues. All right, so that's why we have constraints. Right, the constraints came up with at least one single bedroom. At least 10 bedrooms altogether, but not more than 15. A third constraint, the number of double bedrooms must be at least twice the number of single bedrooms. Always a difficult one to interpret, but we'll do it together. There should be no more than 12 double bedrooms. Let the number of single bedrooms be X and the number of double bedrooms be Y. And the first bit, write down the constraints. Now, before we even write down the constraints from this one, let's write down our implicit constraint. Could we have half a bedroom? Nope, not even single, not even double. So in this case, our x and our y have to be elements of the whole numbers. If you wanted to write integers there, you would be correct, because on your graph, you wouldn't have negatives. A negative bedroom. Doesn't make sense. Of course it doesn't. Let's start again at the top. At least one single bedroom. Single bedrooms are x. So x has to be bigger than or equal to 1. That's our first constraint. At least 10 bedrooms altogether. So singles and doubles together, at least 10. So x's and y's together must be at least 10. At least means can be 10 or bigger. Let's have our next constraint. But not more than 15. So we can't have more than 15, so we've got to be less than or equal to 15. 4 constraints so far, one of them implicit. Let's do this last one and then we can come back to the difficult one. No more than 12 double bedrooms. So double bedrooms must be less than or equal to 12. I suppose 12 double bedrooms would have 24 people. Puts a little bit of strain on your eating facilities, your dining room. Right, let's have a look at this difficult one. The number of double bedrooms must be at least twice the number of single bedrooms. Now, what is that actually meaning? Well, 2x and we have a y. The number of double bedrooms must be at least twice the number of single bedrooms. So it must be at least twice. Can be bigger, but it must be at least. So bigger than or equal to 2x. So y bigger than or equal to 2x. Now there we go. There are all our constraints. Next part of the question. Represent the constraints on the graph paper provided on the diagram sheet, indicating the feasible region by means of shading. All right, so what have we done? We've done our constraints, and now we're going to model them. We're going to make a model of all our inequalities. Well, let's start with the first one. The first one was, and I'll write them over here as we do them, x is bigger than or equal to 1. So what we have is there's our line, our 1, and it's got to be bigger than or equal to 1. I'm just going to make sure that goes all the way up. There we go. Bigger than or equal to 1, so we know that it's going to be on that side of 1. The next equation that we had was x plus y must be bigger than or equal to 10. Right? We had to have at least 10 bedrooms. There we go. Sketched in. That's the smallest, so it's got to be bigger than that. Let's have a look at our next one. X plus y has got to be less than or equal to 15. So here we have 15 over here, coming down, and just going to make sure that that goes over there, so it's absolutely correct. There we have 15. Right, what was our next one? Y has to be less than or equal to 12. Popping in our straight line over here. There we go. What I neglected to do was to put that in, y must be less than 12, and I also neglected to do that over there. X plus y must be less than or equal to 15. Now, the last constraint we had was that y must be less than or equal to 2x. So this has got a slope of 2. So the line would start at 0, 0. And using a test point, for example, I could pop in a 5 over there for x's, 1, 2, 3, 4, 5, and that would intersect at 5, 10 over there. So popping in my line, it's a line that starts at 0, 0 and does that. And it's got to be below that, so it's got to be over here. Right, and the last constraint we got was that y is bigger than or equal to 2x. So y is bigger than or equal to 2x. Now this one, remember, 0, 0 is one of the points, and we're going to have to take another point somewhere on our grid to join the two lines. So I'm going to just choose a point. X is 5, y is 10. The point 5, 10, 1, 2, 2, 3, 4, 5, 10 would be over here somewhere. And that's the point I'm going to use to draw my line with. Right, looking at our constraint, it's above there. I think our feasible region is quite clear. Here it is. And now we've done question 11.2. We've sketched and we've shaded our feasible region. Right, we're going on to 11.3. According to these constraints, could the guest house have 5 single rooms and 8 double rooms? Now remember, singles was x's and doubles was y's. So we're looking for the point 5, 8. Could it be in the feasible region? 5, 8. Let's double check. Well, 2, 3, 4, 5, 8. Is it over there? Is it in the feasible region? Nope, not a chance. So, 5, 8 is not in the feasible region. Therefore, cannot happen. Right, let's move on. Right, 11.4. Here we come to the profit. Rental for a single bedroom is 600 and 900 for a double. Right, 600 and 900. How many rooms of each type should the contractors build so the guest house produces the largest income per night? All right, wasn't profit here. Here we're looking for the largest possible income. Okay, so I'm going to write my income exactly the same. The income is going to be 600x plus 900y. There we go. All we've got to do is go back to our graph, get our vertices, pop them into a table, use our calculator, and see where our income is at a maximum. So we've got our x's, we've got our y's, we've got our income, and let's pop back to our model, our graph, and see what our values are. Well, here we go. We've got the point 112 and the point 19. Popping those down there, 112 and 19. I know you're already saying to yourselves, we don't have to bother checking 19 because it's going to be less than 112, but humor me, we'll do it. We also have this point over here, which is the point 37, and we have the point 510. So 37 and 510. And our last vertex, because there were 5, there it's hiding over there, that'll be the point 312. 312. Okay, let's use our trusty calculator, and we'll have 600 times 1, whoops, 600 times 1 plus 900 times 12. Yep, 11,400. Popping in 9, 8,700. 8,700. Popping in the point 37, x is 3, y is 7. 8,100. Even less. 8,100. 510. Think this is going to give us more. Ah, 12,000. Things are looking up. 12,000. And for the last one, 312. $12,600. How about that? The last vertex, 12,600. So, for maximum income, we're looking for 3 singles and 12 doubles. Please make sure that you write your answer out so that the marker knows that you've analyzed your table and you've got the maximum. I'm going to go back to the question and I'm going to finish reading it because there's a little twist to the tale. They ask us to use a search line. Now the search line is that line that we spoke about earlier, which has a specific slope. Now what you could do is you could work out where you're going to get your maximum profit and then sketch in your search line, or use your search line to work out which of the vertices you're going to test. So I'm going to do the whole question again as if I haven't done the table, but using a search line. So, what was my income statement? My income was 600x plus 900y. Okay, I'm going to take that, put that in terms of y equals. Once I got it in terms of y equals, I can get my slope of my search line. I can pop a search line on my graph and whoop, pop it up and see where I'm going to get maximum income. So solving this, 900y would be equal to negative 600x plus I for income. So y is equal to negative 600 over 900x plus I over 900, which gives me a slope of minus 6 over 9 or minus 2 over 3. So that's going to be the slope of my search line, negative 2 over 3. Let's go back to the sketch and put it in and see where we land up. Right, negative 2 over 3. That's the search line that I'm going to have to be using. Now, I'm sure that you notice that if I use negative 2 over 3, I'll have a very small search line over there. So what I'm going to do is I'm going to say that, and we know that it's absolutely true, is the same as negative 4 over 6. Or how about multiplying everything by 3 and having that as 6 over 9, negative 6 over 9. That's just going to make life so much easier. So 2, 3, 4, 5, 6 over 9. There we go. There's a search line. It's decent size. And now we can slip it up keep it parallel, and see where it goes. Right, there it hits the first vertex. Definitely not a maximum. Moving it up, second vertex, not a maximum. Third vertex, no. Fourth vertex, still not a maximum. And there we go. Smacks the last vertex. And we said that that was the point 312. And yep, that's the vertex which will give you a maximum. And that's the vertex that we also found using our table method and our calculator that we would get a maximum there. So once again, we can go down and write our answer correctly. So at the point 312, we have a maximum. So therefore, income maximized at 3 singles and 12 doubles. Right, and that is the end of the question. What I want to do is I want to recap slightly what we've been doing. You remember that we were always given a story. And from the story, we constructed constraints. From our constraints, we made a model. And from our model, we found our optimal function, or our maximum, or perhaps even our minimum. Now that's the one way the question is usually asked. The other way the question is asked is they give you a model and you have to find the constraints. And from the constraints, you then have to use the optimal function to find your maximum or minimum. I hope that linear programming has made a lot more sense to you and you'll be super successful in your exams.